So this is an example of a solved problem set on well-ordering sets topic. So consider the sets A, B, and C. It is easy to check that all three sets are non-empty, and since they contain only positive integers, the principle of well-ordering guarantees that each of them has a smallest element. These smallest elements may not be easy to find. It is obvious that the smallest element in A is 3. To find the smallest element in B, we need negative 11 plus 7m is greater than 0, which means m is greater than 11 over 7 or is equal to 1.57. Since m has to be an integer, we need m is greater than or equal to 2. Since negative 11 plus 7m is an increasing function in m, its smallest value occurs when m is equal to 2. The smallest element in B is negative 11 plus 7 times 2 is equal to 3. To determine the smallest element in C, we need to solve the inequality x squared minus 8x plus 12 is greater than 0. Factorization leads to x squared minus 8x plus 12 is equal to x minus 2, x minus 6 is greater than 0. So we need x is less than 2 or x is greater than 6 because x is an we determine that the minimum value of x squared minus 8x plus 12 occurs at x is equal to 1 or x is equal to 7. Since 1 squared minus 8 times 1 plus 12 is equal to 7 squared minus 8 times 7 plus 12 equal to 5. The smallest element in C is 5.
Next slide na po. So, the other example of well-ordering principle is prove that every positive integer can be written as sum of distinct powers of 2. So, we will prove this statement using the well-ordering principle. Let S be the set of positive integers that cannot be expressed as the sum of distinct powers of 2. We will assume that S is non-empty and then derive a contradiction. Since S is non-empty, there must be a smallest element n in S. Then n cannot be a power of 2 since that can be expressed as the sum of a single power of 2. Therefore, we can write n as the sum of a power of 2 and a positive integer k less than n that cannot be expressed as the sum of distinct powers of 2. But since k is smaller than n, it cannot be in S. So it must be expressible as the sum of distinct powers of 2. Thus, we have expressed n as the sum of distinct powers of 2, contradicting the assumption that n is in S. Therefore, S must be empty, which means that every positive integer can be written as the sum of distinct powers of 2. So, yun lang. Thank you.